Hi, I am Nononita from PE05 and today I'm going to present my medical electronics project video. This circuit is to represent a heartbeat sound from stethoscope acoustic output which leads to biomedical signal processing circuit. The whole project consists of 4 stages, with stage 1 includes TP1 to TP2 which is the preamplifier stage, and stage 2 which is the closed loop inverting amplifier starts from TP2 to TP3, and stage 3 which is called the active filter starts from TP3 to TP4, and for stage 4, which is from TP4 to TP5, is called the audio amplifier. Stage 1 is called the preamplifier stage. In this stage, IC1A, which is TL072, is a dual low noise Jeff amplifier. This amplifier amplifies small analog signals. Usually, the supply voltage gain is between 10 mV to 1 volt, but it does not provide current. So based on this circuit, it is configured as a fixed gain closed loop non-inverting op-amp. So in this stage 1, C1, the 10 microfarad capacitor, is a coupling capacitor which blocks DC bias voltage from the input and only allows AC signals to pass through. So resistor R5 and R6, which both are 10k ohm, each form a voltage divider which will supply 4.5 volt, allowing op-amp to work in a single supply mode. On the other side, resistors R2, R3 and capacitors C2 and C3 form the bandpass filter. The pass band gain formula, which is 1 plus R2 over R3, is 1 plus 220 kilo ohm over 10 kilo ohm, which is equal to 23. So basically, capacitor C4 is another coupling capacitor which blocks DC from the amplifying signal and outputs clean AC. As we can see the results shown in the table, we can note that as the frequency increases, the gain will also increase. In the table, the gain 24 is the maximum, which is at 100 Hz, equal to 27.6 decibel. So if the frequency is more than 100 Hz, the gain will eventually drop. So based on the frequency response curve, we can learn that the maximum decibel 27.23 minus 3 decibel will be 24.23 decibel. From that frequency 24.23 decibel, we can find our FH and FL. So based on my curve, my FL is 23 Hz and my FH is around 1200 Hz. From that FH and FL, we can calculate our bandwidth, which is FH minus FL, 1200 Hz minus 23 Hz, which will be equal to 1177 Hz, which is the bandwidth. We will set the power supply to 9 volt and put the channel 1 probe at TP1 and channel 2 probe at TP2. As shown here, we have 200 Hz and 200 mV PP, and the VPP is 4.56 volt. We change the frequency to 1 kHz, and as you can see, the VPP will become 3.48 volts. This is the end of stage 1. Moving on to stage 2 is the closed loop inverting amplifier. In this stage, we can see IC1B. They share the same IC as in stage 1, which is TL072. So it is a negative feedback loop amplifier, as we can see in the diagram. Negative feedback loop amplifier means where a portion of the output voltage is fed back into inverting input of the op-amp with a phase inversion which is 180 degrees out of phase. So P1 is the trimmer, which is 100K. The trimmer controls the feedback signal, which can reduce the overall gain of the amplifier. Resistors R9 and R10 acts as the voltage divider, which is the same as in stage 1. They help the op-amp to work in the single supply mode and also acts as a level shifter so that the output will not be clipped. We will put the channel 1 probe at TP2 and channel 2 probe at TP3 to see how the output waveform is. As you can see, after adjusting the trimmer, I put the frequency at 200 Hz and amplitude as 200 mV PP. The output VPP will become 2.88 volt. By adjusting the trimmer, the output waveform will become saturated and sometimes it will be cut off. This time, I will set the frequency to 1 kHz. VPP will become 2.2 volts after adjusting the trimmer. This is the end of stage 2. Stage 3 is the active filter, which still shares the same IC as in stage 1 and stage 2. C5 and C8 capacitors are coupling capacitors. They block out DC voltage, allowing only AC signals to pass through. The resistors R11 and R12 acts as voltage divider, which also acts as level shifter so that no output is being clipped. They also help the amplifier to work in a single supply mode. IC2A, which is TL072, is the Salongi second order low pass filter. It only allows low frequency to pass through while rejecting high frequencies. It is also made up of two low pass RC networks. The lowest frequency that can pass through FL is 0 Hz. So FH becomes the cutoff frequency. So when we want to calculate the bandwidth, FH minus FL is equal to FH minus 0 Hz. So the bandwidth becomes the cutoff frequency, which is FC. We can determine FC by this equation, 1 over 2 pi square root of R7, R8, C7, and C6. The value we will get is estimately 995.925. When we round up, it will become 996 Hz. Based on the table of outputs below 500 Hz, the gain is at unity. And as you can see, when the frequency is above 500 Hz, gain and Vout will eventually drop. Based on the frequency response curve, minus 3 dB line will be at negative 3 decibels. So FH will be at 1.2 kHz. So when we want to find the bandwidth, FH minus FL is equal to 1.2 kHz minus 0 kHz, which will be 1.2 kHz. Now we will test the output waveform at DP4. I will put the settings at 200 Hz and 200 mV PP. VPP at DP4 will be 2.84 volts after being trimmed. Now I will change the frequency to 1 kHz and see what happens. As mentioned earlier, frequency below 500 Hz will be a unity gain, but in this case when we change to 1 kHz, the unity gain is not applicable. So there will be an output voltage drop at DP4. This is the end of stage 3. Moving on to stage 4, we can see that IC3, which is LM386N-1, is being used. The IC LM386N-1 is an audio amplifier that drives the speaker. It also acts as a compact low-power amplifier that boosts tiny biosignals such as heart sounds. It is a single supply mode internally, hence no voltage divider is required. It also drives the current to the speaker. Capacitor C13 is a coupling capacitor which blocks DC bias voltage and only allows AC bias voltage to pass through. This ensures that only the AC part of the sensor goes into the amplifier, avoiding any DC bias voltage from the sensor. Capacitor C15 stabilizes the amplifier and suppresses high-frequency noise. It filters out high frequency, which is above 40 kHz. This ensures that audio signals will remain clear and undistorted when sent to the output stage. Without it, the output waveform will also be unstable. The input will go through the trimmer P2, where pin E has full amplitude, and PS and PA, which has 0 amplitude. We will now test the output waveform at DP5. We will set the frequency to 200 Hz and amplitude to 200 mV PP. The output voltage will be around 7.04 volts. Then we will set the settings frequency to 1 kHz. As we can see, the output voltage at DP5 will be 3.36 volts. By adjusting the trimmer P2, we can also control the output at DP5. This is the end of stage 4 and the project video presentation.